Good afternoon. Thank you for attending. Let me see if I can make this work. So what I'm going to do is go over sort of the basic ideas of meta-analysis, the premises, talk a little bit about some of the resources from the Brain Map project, and show you some of the more advanced applications as well, so try and do the whole scope, and then leave it to the subsequent speakers to go into more detail. And there we go. Okay, so the field as a whole is based on the original notion of Jean Taylorac, a neurosurgeon, to put observations into standardized coordinate space. At about this same time, people at the Montreal Neurologic were doing stimulation and cortical recording, but they were just drawing it on a picture of the brain with no coordinates and no other references. It's just that neurosurgeons always know where they are, and so they just put X's where their observations were and have the nurses write them in hand on the piece of paper, and that was their documentation. And Taylorac thought that that was a bit impoverished and put it into a standardized space and developed the stereotactic reference frame and started recording his own data. And he published a good amount in these atlases and also in his own publications, recording probabilistic anatomy both structurally and functionally. And so the whole field started with his notion of probabilistic anatomy. So what's shown there here is functional recordings. That's from cortical stimulation, and these are from pneumoencephalography, and they're showing the variability in sulcal location. So having been exposed to that by a visit to Paris, I worked to put together a fairly simple 9-parameter algorithm, and in part that was because it was simple, and in part I didn't know any better, but it turned out that 9 parameters captures the huge majority of the variance, and that algorithms which have added additional parameters have added only a small amount to correcting for the inter-individual variability. One of the big things that this does for us all is signal averaging, and so this is a graph of the noise suppression. As you add more subjects together, you drive the noise down, whereas the signal stays constant. And so you can get findings to emerge from the noise through the basic principles of signal averaging. So this is an old observation, but it remains true, and all of us use it every day. So one of the things that helped a great deal in promoting this whole field was that the group in London adopted this standard and promoted it with their SPM software, and so they were the first to adopt it generally and distribute this as freeware. And so others have followed. So FSL does this, AFNI does this, pretty much everyone does this now. And what that's resulted in is more or less 50,000 publications that all use standardized coordinates, all referenced to the same coordinate scheme, more or less. So there's lots of data here. So that's showing something like 50 finger tapping experiments, and you can see that the coordinates cluster more or less. And if you squint, you can sort of see where different functional locations are. But we don't really want to have to squint at our data. So Peter Turkeltaub figured out a squinting algorithm that looks at the data and kind of fuzzes it together and brings out the consistent co-occurrence patterns. So this was the first really quantitative whole brain algorithm to do meta-analysis on coordinate-based data. So Peter on this paper has over 1,000 citations now. This was his part of his PhD dissertation work at Georgetown. And I was quite thrilled to see, before I get there, this algorithm was released in 2002, and it's been steadily evolving ever since by a number of groups. my group, Simon Eichhoff's group, Peter Turkeltaub continues to add to this algorithm. And for this, in April, he received, well-deserved, the Norman Geschwin Prize in Behavioral Neurology, specifically for the contribution that Ale has made to our understanding of the functional organization of the human brain. So there you go. Even the neurologists understand how important meta-analysis is to our collective understanding of the brain. So this is a tool you'll hear more about later. This is the brain map meta-analysis environment. This basically hard codes all the experiments, describes the experiments in fairly detailed terms, both for functional and structural data, keeps them in an Oracle database online. You can search it and download it, and you can compute meta-analyses using variations of the Ale algorithm. When I say it's hard-coded, it has a lot of metadata associated with it that is put in by hand with a variety of different metadata fields. Behavioral domain is one, so it's sort of an overview taxonomy of which cognitive operations are recruited. And online, there are computations, live meta-analyses that get updated as we grow the database, both for the behavioral domain. So here it's showing cognition, language, orthography as one domain, and so this is the collective map. It's showing viewing affective pictures as a paradigm, and this is the map. So there are a couple of hundred of these available online, and it shows you which experiments went into them so you can edit them and modify them yourself. One of the spin-offs of this is shown here. It's meta-analytic connectivity mapping. And what this is doing is taking for any brain region, asking the question, when this region activates, what else activates with it? What co-activates with this? And you can use this to build maps of functional connectivity. These have been validated in various ways. This is a step up in granularity from a MACM, which is typically done with a region of interest. This is done voxel-wise. This was done by Danilo Buzdak, and it's showing the connectivity-based parcellation using the MACM algorithm, which is in turn the same as the Ale algorithm, to segment the amygdala and validate this against cytoarchitectonics. So when we say we're getting at functional connectivity meta-analytically, this is at a very fine grain, despite the fact that the data is just published as per experiment activation coordinates. This is a very widely cited paper that shows the comparison between resting state network, shown here as RSN, and brain map, shown here as BM, with an ICA decomposition of the entire brain map database, showing that task activation data follows the same network structure as resting state data. And I'll come back to this in a little bit. With resting state data, obviously you have no behavioral information, but brain map has it, so you can use the brain map metadata to interpret resting state networks. And so that's what's done here. It's a heat map of those 10 ICA components I just showed you. By the behavioral domains, we also have this for the paradigm classes. And most recently, we've added disease categories to this. So this is actually widely used to interpret resting state networks. The next level of analysis, these are all tools built on Ale, but there are many other computational tools which you can apply to your data. One very popular tool is graph theory. And so this is showing a comparison between graph theory performed on the brain map database here and graph theory performed on resting state data. And they produce very similar answers. So one of the implications of this is that you can apply graph theory meta-analytically. And you can expect it to predict your primary functional data. You can do another approach to doing this is to use structural equation modeling and build node and edge models. So we've taken brain map and built node and edge models and then compared them to resting state data from individual subjects. and they strongly predict the path coefficients in a structural equation model. So your meta-analytic models can become priors for your analysis of your primary data. This is also a widely used application. So another class of literature that also uses coordinates is voxel-based morphometry, originally described by Ashburner and Friston in 2000. This is a very widely used technique. This paper has now over 5,500 citations. So it's a big literature. And it specifically is describing in this coordinate space the disease-related atrophy. And so this is showing one of my favorite papers showing voxel-based morphometry in Huntington's disease done by covariates with different indicators of disease progression. There are a number of well-cited papers that do this meta-analytically. One is shown here. This is a recent paper in JAMA Psychiatry doing a meta-analytic approach using AO and MACM to psychiatric disorders, showing what they have in common. And basically, this is arguing using these meta-analytic data, you can compare across multiple diseases, whereas virtually no clinical trials span all the different psychiatric disorders. So every data set is in a disorder, whereas this data set is across all disorders. So you can start drawing conclusions about transdiagnostic and diagnosis-specific effects and discriminating those. And it turns out that in psychiatric disorders, much of the pathology is transdiagnostic and not diagnosis-specific. So this is something, honestly, you can only do by meta-analysis. Bullmore's group, Nick Crosley, did this as his PhD research. Notice that Brain, which in its instructions to authors says it doesn't want meta-analyses, no meta-analyses need apply, let this one through, and it's now the second most highly cited Brain article in the last 3 years. So if you're looking for something that has high impact, look at meta-analyses. They tend to be very highly cited papers. The message of this was similar. It was that psychiatric disorders are transdiagnostic, but further, that they selectively affect hubs. So any pathology that hits connectomic hubs is going to produce symptoms. This kind of approach can also be done meta-analytically using structural equation modeling as well as graph theory. And this, as a paper that we're about ready to send in where we did in Alzheimer's disease, structural equation modeling meta-analytically, and then we fit the model to the ADNI data in Alzheimer's disease and are getting very tight fits and using this to generate biomarkers for the primary data. And then as a final direction, I showed you the functional ICA and comparison to resting state. So this is now a comparison of the two brain map databases, the structural and the functional, using the same algorithm. So it turns out that if you look at the functional database and you get out the canonical ICA components and you do exactly the same thing to the structural data, you get out the same components. The concordance is even higher than that between the structural data, the functional data and the resting state data. So it's telling us that pathology follows these networks and that we can use the functional data and the functional metadata to interpret the disease effects in diseases, neuropsychiatric diseases causing brain atrophy. So just to summarize, so coordinate-based meta-analyses can be used for network modeling. They apply to functional and structural data equally well. Although we start with MACM, AL, and MACM, you can apply other constructs quite effectively. ICA, graph theory, structural equation modeling, all can be applied both meta-analytically and to primary data. I didn't go through many of the validations, but there are quite a lot of validations of this overall approach using primary data. And I know this was fast, but if you want to get deeper in this, first you have the rest of the workshop. But also, there's a summary article in Annual Reviews of Neuroscience that Jack Lancaster, Angela Laird, and Simon and I put together a couple of years ago. And I'll stop.